Hi, everybody. It's Mr. Haney, and we are going to talk about fission and fusion today. Just a couple of quick notes. There are 8 seniors total in my classes. Seniors, you got to get your trash done in a hurry. You are out of time. All right? Seniors, if you want me to grade all your work, you got to have it to me by Friday. Okay? Well, I'll give you the weekend. I got to have it by Monday, okay, of next week. You got to give me all your work by Monday of next week if you're a senior, because you have to take finals next week, okay? Grades are due for seniors on Friday of next week. I'm going to give them to you on either Tuesday or Wednesday of next week, so I have time to get them all graded. And you have plenty of time to take them. I haven't really figured out which day I'm going to do it yet, Tuesday or Wednesday, but get it done. The rest of you, all of your late work is due. Let's say 2 weeks from today. So not next Monday, but the Monday after. Okay, that's when the late work is due. All right. That way I've got 3 or 4 days to get everything squared away and taken care of. You've got time to get ready for your finals in my class and in other classes and whatnot, just to get it done. All right. So, you know, we got to kind of step up on the game here and get some stuff done. You're running out of time. There's only, what, 17 days left? Something along those lines. So snap to it. So let's talk about fission and fusion here. Fission is breaking an atom up into a nucleus, into smaller fragments. So this is what we use for powering nuclear reactors. You take uranium-235, plutonium-239. These are considered fissionable materials because you can break them up. You get a lot of energy out, and the byproducts are manageable. These atoms break into 2 fragments that are roughly the same size. It's not like you split it in exactly half. It's kind of like when you make a peanut butter and jelly sandwich and your mom says you have to give half of it to your little brother or sister because they're being a butt, and you have to share, and you're like, oh my gosh, I'm so tired of sharing with this little midget. Fine, you want half my sandwich? Fine. And you cut it in half, but it's not exactly half. It's more like a 60-40 or a 1/3, 2/3. They get part of your sandwich, but they don't get half. Be honest, we've all done it. I've done it to my kids. That's good parenting. Sorry. So these 2 things, they're not quite the same size. You get one that's a little bit bigger than the other. But they break in half when they get hit by a slow-moving electron. And that releases 2 more neutrons. I'm sorry, it says electron. It should be neutron. I'm sorry. Here, let's fix that. My bad. Slow-moving neutron. Helps if I can spell. Okay. There. Yeah, there we go. Slow-moving neutron. Now it makes sense. Like electron, what the heck? What that does is it gives you 2 more neutrons that go out and they strike more uranium-235 or more plutonium-239, whatever it is. So now you've got 3 neutrons out there breaking these bad boys into pieces. Okay? And then they go out and they release more neutrons. After they hit other atoms, they break up and the neutrons are released. This continual release of neutrons perpetuates the fission process, and it's called a chain reaction. All right? Because 1 becomes 3, becomes 9, becomes, and it just keeps on getting exponentially bigger. Okay? And this releases enormous ridiculous amount of energy. Because again, uranium is radioactive. It releases a crap ton of gamma rays. When you break it in half, you're breaking the strong and weak nuclear forces into pieces. You're releasing a huge amount of energy. 1 kilogram of uranium releases the same amount of energy as 20,000 tons of dynamite. That's 4 million pounds of TNT going boom all at once. That's a lot of energy. Okay? Now, uncontrolled chain reactions occur in atomic weapons or nuclear weapons. This is when you don't have anything to control the reaction. It just goes as quickly as it can and big bada boom. Controlled chain reactions occur in nuclear reactors. Okay? Now, in a nuclear reactor, most of this energy is released as heat, which is then used to generate steam and drive turbines to generate electricity. And it's relatively clean. It's zero carbon emissions. It does not affect the greenhouse gases or anything like that at all. It does give you some nuclear waste that you have to store. But if you're smart, and this is one place I got to give France some credit, France builds recycling facilities on site of every nuclear reactor. So the used uranium rods or used plutonium rods go from the reactor core straight to the recycling plant, where they are recycled, repurposed, and they have an 88%, I believe, 88% recovery. So they have 12% waste, which is amazing. Okay, you take 100 pounds of radioactive material and you only have to store or dispose of 12 pounds. That's miraculous almost. Here in the United States, all we do is we drive it over to Nevada and we store it under a mountain. We're not worried about recycling because that's just crazy talk. But what they do is they have these cadmium control rods. Cadmium is kind of like a nuclear sponge. Okay, cadmium has this weird little property where it can absorb neutrons out like crazy. Okay, like putting a sponge on a spill on your counter, it just sucks it up. Cadmium does the same thing to neutrons in the nuclear reaction. So what it does is it absorbs neutrons to slow the reaction down, to keep it regulated, to control how much heat is generated, how much energy is released. You can pull the rods all the way out, and the reaction goes crazy and it goes critical. And boom, you can slam them all the way down and shut everything off. Okay. Part of this is one of the things that happened at the Chernobyl nuclear site in Russia way back in the 80s or 90s. I forget when it was exactly. Here in the United States, we have 4 backups. You have the primary, and then you have 3 backups to make sure that things like what happened at Chernobyl don't happen. What happened at Chernobyl is the primary failed, the backup failed, and it generated a lot of heat. It evaporated all the water in the reactor core that's helped, to generate steam and whatnot. So you got way too much steam. It overpressurized the dome, which was just a concrete dome. It wasn't anywhere near up to snuff with what we've got here. And it was actually a physical explosion, not a nuclear explosion. But that physical explosion caused huge environmental damage to the area around Chernobyl, and it sent radioactive clouds, radioactive steam and whatnot all over the world. It's a bad thing. Now, fusion, that's all fission. That's what we currently do. Fusion is when you take 2 nuclei and combine them into a nucleus with a heavier mass. Okay? And this generates an awful lot more heat than fission does, because this is what powers the sun. All right? So it's really not that complicated to figure out. but this gives you an awful lot more heat. In the sun, you take 4 atoms of hydrogen, they fuse together to make 1 atom of helium. That generates enough heat energy to power a star. Now, we've got some really brave scientists here on Earth who are trying to duplicate that on a much smaller scale and produce fusion reactors here, because we can generate all the hydrogen gas we want by electrolysis of water, separate hydrogen and oxygen in water. They haven't done it yet because fusion requires such high temperatures and high pressures. It requires a temperature of roughly 40 million degrees Celsius. The closest I think we've come so far is the Takamuk reactor in Japan, which uses just these incredibly huge electromagnets to generate high energy plasma. And the last time I looked, they were somewhere in the neighborhood of 30 million degrees Celsius. And it's been a while since I looked it up. But they're getting really, really close to being able to pull this off. Okay? If they make fusion possible, you have a process where your only byproduct is helium, so all the little kids in the world get balloons. Nothing wrong with that. Everybody gets balloons for everybody. You get free energy, basically. You know, it's every global warming, climate change believer's dream job right here, is if they can make this work. And there are scientists, they've spent their careers trying to make this work. So, you know, before you say science isn't doing anything, yeah, they actually are. It's the size of the hurdle you're trying to surmount that's the problem. So that's all we're going to talk about with fission and fusion right now. Fission is breaking the atom apart. Fusion is putting them together to make bigger atoms. That's really all you need to know. Tomorrow we're going to talk about some of the things we've done with fission and fusion. Okay? So today, your homework is crank out all of your missing assignments. I know you've got a ton of them because I'm the one with the grades. I've got tests that haven't been done. I've got labs that haven't been done. And if you have to do something, those are the 2 places I start with because they make the biggest effect on your grade. They have the biggest effect on your grade. Start with your labs and tests. Do those first. Then worry about the homework, because homework is a small portion of your grade. It'll bring you up a little bit, but the tests and labs will bring you up huge amounts, leaps and bounds. Get them done. I'm giving you the day to do that, especially you seniors, because you're out of time. Okay? Do your work. Bye, y'all.